Hey, welcome back. You ever see a headline about a new drug or a new diet and wonder, is this for real or was it just a lucky fluke? Well, there's a powerful little tool that scientists use to tell the difference. It's called the p-value. And today, we're going to pull back the curtain and demystify it once and for all. Let's get right into it. So, let's set the scene. Imagine a school tries out a brand new, cutting-edge teaching method. And at the end of the year, the students in that group have way higher test scores. Awesome, right? Well, maybe. Here's the big question, the mystery we have to solve. Was that improvement real? Or did that group just happen to be a little sharper? Or maybe they just got lucky on test day? Is it a fact or is it a fluke? All right, so to crack this case, we need to look at how the school set up their investigation. You can't just guess, you need a solid plan. So let's see how they did it.
They did a classic head-to-head comparison. Super simple. They took a bunch of students and just split them in two. Group A, they get the old traditional teaching style, the stuff that's been used for years. Group B, they get the shiny new method. And the goal is dead simple. At the end, we compare the test scores from both groups and see if Group B actually did any better.
Okay, so you've got your two groups, you've got your scores. Now what? How do you decide if the difference you see is meaningful? Well, this is where researchers bring in their secret weapon. This is where the p-value finally enters the scene. So what in the world is a p-value? Honestly, the easiest way to think about it is as an evidence meter. That's it. It's just a number, usually something small like 0.04 or 0.25, and its whole job is to tell you how strong your evidence is. Specifically, it measures evidence against the idea that nothing happened. It tells you how surprising your result is.
You see, in any experiment like this, you're always weighing two competing ideas. The first one is called the null hypothesis. That's just the skeptical default idea. It basically says, nope, the new method goes nothing. Any difference is just random noise. But on the other side, you have the alternative hypothesis. That's the exciting idea you're hoping is true, that the new teaching method actually works and improves scores. The p-value is what helps us choose between these two stories.
So, how do we get that p-value? How do we go from a bunch of test scores to a final decision? Well, researchers follow a really logical 5-step investigation. And don't worry, we're not going to do any math here. This is all about understanding the thinking, the logic that gets us to the truth. So here's the game plan. Step 1, we already did. We set up our two competing ideas, the null and the alternative. Next, you got to choose the right tool for the job. Then you collect your data, the test scores, and run the numbers. That calculation gives you the all-important p-value. And the final step? You just compare that p-value to a finish line you set at the beginning, and you make the call.
And just so you know, scientists have a whole toolbox of these tests for different situations. If you're comparing categories like yes or no, you might use a chi-square test. If you have like 5 groups to compare, you might use something called an ANOVA. But for our school's simple case, just comparing the average scores of 2 groups, the perfect tool for the job is called a t-test.
Okay, the moment of truth. The school has run their t-test, the numbers have been crunched, and the investigation is officially complete. So, what's the verdict? Did the new teaching method actually work? And here it is, the big reveal. After all is said and done, the p-value from the school's experiment is 0.03. Okay, so it's a number. What does that actually tell us? What does 0.03 mean for the school, the teachers, and the students? Let's translate this. This is the absolute key. A p-value of 0.03 means this. If the new teaching method was totally useless, if that null hypothesis was true, there would only be a 3% chance of getting results this good or even better, just by pure random luck. Think about that. A 3% chance is pretty darn unlikely. Our result is pretty surprising. So, how unlikely is unlikely enough? Well, researchers decide that before they even start. They set a cutoff point, a line in the sand, called a significance level, and almost everywhere that line is set at 0.05, or 5%. So all we have to do is compare. Our p-value is 0.03, the bar was 0.05, and since 0.03 is smaller than 0.05, we cleared it. Because we cleared that bar, we get to make an official scientific statement. It sounds a little dramatic, but we get to reject the null hypothesis. In normal English, we're throwing out that skeptical idea that the new method did nothing. We have enough evidence to say that the improvement we saw was the real deal. It was a fact, not a fluke. Mystery solved. So that's great for the school. But what's the big picture lesson here? Let's zoom out for a second and lock in the one thing that you absolutely need to remember about p-values, no matter where you see them.
If you only remember one thing from all of this, let it be this right here. The smaller the p-value, the stronger the evidence. That's it. A really tiny p-value, like 0.001, is screaming at you that your result is significant. A larger one, like 0.30, is kind of shrugging its shoulders and saying, could just be random chance. Lower is stronger. It's really that simple.
And that kind of leaves us with a final thought. This whole idea isn't just for people in lab coats. It's a way of thinking. You see a new workout that promises amazing results. You try a new diet. You try a new way of organizing your day. How do you know if it's actually working or if it's just noise? What fluke or fact mystery out there in your own world is just waiting for you to solve it?